Hello everyone, I am Akanksha. We are presenting our project titled IoT based Smart Toll System, a real time location approach for automatic toll processing. We have created this project under the guidance of our Dean, Dr. Naveen Kumar sir. In today's world, toll collection system often lead to the traffic congestion, long queues and delays. Our project aims to solve these problems using modern technologies like IoT and GPS. Our project, IoT based Smart Toll System, focuses on improving traditional toll collection methods using GPS and IoT technologies. In the current system, vehicles must stop at the toll plazas, which leads to the traffic congestion, long waiting times, fuel wastage, and delays. To overcome these issues, we propose a smart and automated toll collection system. The system is integrated with the IoT and cloud technology, which leads to the real-time communication and processing. The calculated toll fee is automatically deducted from the user's registered account, eliminating the need for the manual toll booths. Additionally, the system provides a transparent interface where a user can view their travel distance, toll charges, and transaction details. This improves trust and accountability. It also supports digital payment systems like FASTag and contributes to the development of the smart transportation infrastructure. Overall, our system offers a scalable, efficient, and user-friendly solution for the modern toll collection. Objectives. The main objectives of our project are as follows. First, to develop an automated toll collection system that eliminates the need for the manual toll booths. Second, to track the vehicle movement accurately using the GPS technology. Third, to calculate the toll charges based on the actual distance they traveled, ensuring the fair pricing system. Fourth, to enable the real-time data communication using the IoT and cloud technology. Fifth, to automatically deduct the toll fees from the user's registered account. Finally, to reduce the traffic congestion, waiting time, fuel consumption, and improve the overall efficiency of the transportation systems. Proposed system. Our proposed system is designed using the GPS and IoT technology to automate and improve the toll collection process. First, the system uses the GPS to continuously track the real-time location of the vehicles. It identifies when a vehicle enters and exits a highway without requiring any physical toll booths. Next, the system calculates the total distance traveled by the vehicle using the GPS data. This ensures accurate measurement of the journey. Then a microcontroller such as Arduino processes this data and calculates the toll amount based on the distance traveled. This provides a fair and usage-based pricing system. The calculated toll amount is then automatically deducted from the user's registered digital account, eliminating the need for stopping at the toll plazas and reducing the waiting time. Additionally, an LCD shows important information such as travel distance and toll charges, ensuring the transparency for the users. With the help of the IoT and cloud integration, the system enables real-time communication and data processing, making it efficient and reliable.
My name is Samiksha and I'm here to explain you about the hardware components of this IoT project. The proposed IoT project Smart Toll System consists of several key hardware components that work together to enable real-time vehicle tracking and automatic toll collection. The primary component used in the system is the ESP32 microcontroller, which acts as a central processing unit or the brain of the entire system. The ESP32 is a powerful, low-cost microcontroller with built-in Wi-Fi and Bluetooth capabilities, allowing it to connect directly to the internet without requiring additional modules. In this project, the ESP32 is responsible for receiving the location data from the GPS module, processing the data to calculate the distance traveled, and transmitting the processed information to the Firebase cloud database. Its high processing speed and integrated communication features make it ideal for the real-time IoT applications. The next component is a Neo 6M GPS module, which is used to obtain the real-time geographical location of the vehicle. This module communicates with the multiple satellites orbiting the Earth and determines the exact position of the devices using a medical call triangulation. It provides essential data such as latitude and longitude, which are continuously read by ESP32 through serial communication pins. The GPS module plays a crucial role in detecting when a vehicle enters or exits a specific toll zone and enables accurate distance calculation based on the movement. To ensure portability and continuous operation, a lithium battery is used as a power source of the system. Since the device is intended to be installed in moving vehicle, it cannot rely on a constant external power supply like a USB connection. The lithium battery provides a stable and rechargeable source of energy to both the ESP32 and GPS module, allowing the system to function independently. Additionally, connecting wires are used to establish electrical connection between ESP32 and the GPS module. These wires carry both power and data signals, ensuring proper communication between the components. A USB cable is also used during development to upload the program from the Arduino IDE to the ESP32 and to the monitor output through serial communication. Once the code is uploaded, the system operates independently using battery power. Here, in this diagram, we are using four main pins from Neo 6M and the ESP32 sensors. So the first pin is VCC from GPS module, that is Neo 6M, and ground, TX and RX. VCC stands for voltage common collector, GND stands for ground pin, TX stands for transmit, RX stands for receiver. And firstly, the VCC from Neo 6M is connected to the ESP32 3.3V pin. The ground pin in the Neo 6M is connected to a ESP32 ground, and the TX in Neo 6M is connected to the GPIO 16 of ESP32, and the RX in Neo 6M is connected to GPIO 17 on the ESP32. So it is basically for the power supply, and it sends data to ESP32 and receives the data from ESP3. During programming and debugging, a USB cable is used to connect the ESP32 to the laptop. This connection allows the Arduino IDE to upload the code into the ESP32 flash memory and also enables the serial communication for monitoring real-time output through serial monitor. Once the code is successfully uploaded, the USB connection can be removed and the system continues to operate using the battery supply. Overall, the connections are simply yet crucial, involving proper power supply, wiring, and serial communication links, ensuring both smooth data transfer from the GPS module to the ESP32 and enabling the system to perform a real-time tracking and a toll calculation effectively.
Now I'll explain how all the components are connected. First, the GPS module collects the live location of the vehicle. This data is sent to ESP32, where the Arduino code processes it. Then the ESP32 uploads this data to the Firebase real-time database using Wi-Fi. The web application built using HTML, CSS, and JavaScript is connected to the Firebase and continuously reads this data. Whenever the data changes, the dashboard updates automatically, showing distance, toll amount, and location details. This is how it flows: GPS to ESP32, ESP3 to Firebase, then web app, then user dashboard. Before moving to the Arduino part of the project, we have created a database using Firebase. It includes static points like latitude, longitude, and also entry and exit point, that is MRUH ground to MRUH parking. And it also includes total toll cost and distance traveled. And this Firebase is connected to both ESP32 and the web application. The USB 3.2 of the kit is connected to the laptop or PC using USB cable. Then we open Arduino code to write code. This Arduino code include the main libraries like Wi-Fi for internet connection, Firebase ESP32 for cloud communication, Tiny GPS++ for reading GPS data, and Vector to store multiple checkpoint location. First, the ESP32 connects to Wi-Fi using the given SSID and password. Then it connects to the Firebase real-time database using the host URL and authentication key. After establishing the connection, the system loads predefined checkpoint location from Firebase. These checkpoints contain latitude and longitude values are used to detect entry and exit points. In the loop function, the GPS module continuously provides live location data in form of latitude and longitude. This data is sent to the Firebase under the live tracking section. Enable real-time vehicle tracking. Next, the system checks whether the vehicle is near any checkpoint within a distance of 30 meters. If a checkpoint is detected for the first time, it is marked as a entry point. When another checkpoint is detected, it is considered as the exit point. The system then calculates the distance between entry and exit using a distance formula. Based on the distance, the toll cost is calculated using a fixed rate.
Finally, the calculated distance and toll cost are uploaded to Firebase, which is then displayed on web dashboard. Here is the HTML part of a project. The HTML file, which is index.html, defines the complete structure of the web application. It includes different sections such as login page, dashboard, trip details, and payment model for QR codes. I have used basic HTML tags. Then I have also used important IDs such as login form and dashboard to control visibility. Distance and tool to display real-time values. Entry latitude and exit latitude for coordinates. Pay button for triggering payment. These IDs are very important because JavaScript use them to update data dynamically. App.js connects the web application to Firebase real-time database and handles all dynamic operations. It performs login validation using input IDs, fetching real-time data from Firebase, and also updates HTML elements like distance, toll, and coordinates. It also handles pay button click, QR code generation, and also pay success displays. This is how we run the code. Once we start running the code, it gets compiled to the ESP32. It takes some time to get uploaded. Once you see the successful message, you recheck the Wi-Fi and the Firebase connection. Then if everything is successful, then we go to web page code. Then on HTML page, we'll run it on live server. Here's the dashboard of our project. We can log in with our valid credentials. Here we can see distance traveled and the total amount, the longitude, latitude of the entry and exit points from GPS, Neo-GL6M module. The distance is calculated based on Havrin's. Then when you click on pay on, there will be a pop-up message of QR code. When you scan and pay the amount, if the payment is successful, you will see an payment successful message. When you click on done, will you can log out or welcome to your toll booth. This page will be pop up. This is how our project works.